You know, some of the most beautiful colors we see every day are created by a trick of physics, a trick that starts with a question that sounds, well, completely impossible. So let's start right there. What happens when you add light to light? I mean, you shine a flashlight on a wall, you get a spot of light. You add a second one, you get a brighter spot. Simple, right? It's just common sense.
But what if I told you that sometimes when you add light to light, you get nothing? Total darkness. How on earth is that possible? Well, it's not a magic trick. It's physics. And it's a phenomenon that totally flipped our understanding of what light even is.
So this bizarre outcome has a name. It's called interference. And it's the key that unlocks a fundamental secret about light. That it doesn't just behave like a stream of particles, it acts like a wave. And waves, well, they have rules. Okay, that is the official textbook definition, and wow, is it a mouthful. Let's just push that aside for a second and think about something simpler, like ripples in a pond. When two waves of ripples meet, they don't just ignore each other, right? They interact. One moment they're taller, the next they're flat. That's all interference is. It's just what happens when light waves do the same thing. The energy doesn't disappear, it just gets moved around.
Now, you can't just take any two flashlights and expect to see dark spots. There's a catch. For this to work, the light waves need to be what scientists call coherent. The best way to think about it is like two dancers in perfect sync. Every step, every move is perfectly aligned. They have a constant phase relationship.
And when these synchronized light waves meet, one of two things is going to happen. If the peak of one wave lines up perfectly with the peak of another, they combine and get even stronger. That's constructive interference, and that's your brighter light. But, and this is the cool part, if the peak of one wave lines up with the valley of another, they completely cancel each other out. That's destructive interference, and that's how you add light to light and get pure darkness.
And if we were to map this out, you'd see this pattern of high and low energy. The high points, the peaks, are those bright spots where the waves are building each other up. But those points that hit the zero line, that's where the magic happens. That's perfect cancellation, total darkness. Remember, the energy didn't vanish, it was just taken from the dark areas and pushed into the bright ones. Now, this whole idea was so weird, so against all intuition, that it took a truly brilliant and surprisingly simple experiment to prove it. And this experiment became one of the most important in the history of science.
So, let's jump back to 1801. For ages, the biggest minds in science, including Isaac Newton, argued about light. Was it a particle, or was it a wave? Then a polymath named Thomas Young came along. He decided he was going to settle this argument for good. And what he discovered changed everything.
This is his setup, and it's just beautiful in how simple it is. Young thought, okay, if light is just a bunch of tiny particles, like microscopic paintballs, and I shoot them through two little slits in a wall, I should just get two splats of paint on the screen behind it, right? But that is not what he saw. Not even close.
Here's the play-by-play. First, you pass light through one slit. That just cleans it up, makes it orderly. Then that light hits a barrier with two more slits right next to each other. And this is the crucial part. Those two slits act like two brand new, perfectly synchronized, coherent sources of light, just like our two dancers. From there, the two new waves spread out, overlap, and, you guessed it, interfere with each other before hitting a screen at the back.
So what did he see on the screen? Not two simple lines. He saw this wild pattern of many alternating bright and dark stripes. We call them fringes. The bright stripes were where the waves added up constructively, and the dark stripes, that's where they canceled each other out destructively. This was it, the absolute, undeniable proof that light behaves like a wave.
And what's so amazing is that this isn't just some weird thing that happens in a physics lab. Once you know what you're looking for, you start to realize interference is happening all around you, all the time. It's responsible for some of the most beautiful things we see.
You ever look closely at a soap bubble and see those incredible, swirling rainbow colors? Or the same kind of shimmering pattern in an oil slick on a wet road? How about the absolutely stunning colors of a peacock's feather? Yep, all of that is interference in action.
It's all because of something called thin film interference. Let's take that soap bubble. When light hits it, some of the light wave bounces off the very top surface, but some of it actually goes through the thin soapy film and bounces off the bottom surface before coming back out. That second wave had to travel just a little bit farther, and that tiny delay is all it takes to knock the two waves out of sync.
They interfere, canceling out some colors and boosting others, which gives you that beautiful, shifting rainbow.
Okay, so interference is beautiful, for sure, but it's also ridiculously useful. It didn't take long for scientists to realize that if this wave behavior is so predictable, maybe they could use it to measure things with incredible precision. And this is the machine they built to do it, the Michelson interferometer. The concept is genius. It takes a single beam of light and splits it in two. It sends those two beams on a race down two different paths. They bounce off mirrors at the end and then are brought back together. If the two paths are exactly the same length, the waves come back together perfectly in sync. But if one path is longer than the other, even by a microscopic amount, they'll be out of sync and create an interference pattern. By reading that pattern, you can measure distances you can't even see.
And the things we can do with this are just mind-boggling. We can measure the exact wavelength of light itself. We can detect vibrations smaller than an atom. Astronomers use interferometers to get super sharp images of distant stars. And get this is the very same technology used by the LIGO observatories to detect gravitational waves, actual ripples in the fabric of space-time, from black holes colliding billions of light years away. All of that just from adding and subtracting light waves.
So think about that. We started with a question that sounds like a riddle. How can light plus light equal darkness? And the answer revealed the true wave-like nature of reality and handed us a ruler precise enough to measure the cosmos. It really makes you wonder, doesn't it? What other huge secrets about the universe are hiding right there in front of us, just waiting for us to ask the right, simple question?